Hi everyone, welcome back to the channel. In this video we will learn linear algebra, which is the core foundation for building any real world AI system. And linear algebra help us understand how data is processed, how neural network process the information, and how model like ChatGPT, YOLO and recommendation system work under the hood. This math is not negotiable if you want to learn full stack AI engineer, but don't worry, I will make it simple, visual and practical. And so I will be using PPT so that you can visualize it clearly and you can understand step by step where AI is being used here. So let's begin. So that is a PPT here, and you will see that the first page that is saying that is learn only the math that actually power machine learning, deep learning, computer vision, LLM, RAG and attention. So that is what I am saying about before as well, that is linear algebra. So why linear algebra is the core of AI? So AI model do not think, they calculate. So neural network are matrix multiplication. So I will keep it short, but I will explain everything. So that's like images, text, audio are converted into numbers, understanding matrix, understanding AI internal. So what they are saying, that is, if you look at the computer itself, that computer does not understand human language itself, but they understand the binary like 0 and 1. So in terms of model as well, if you look at the AI itself, they understand the matrix means math very well. So the behind the math is very important, and that's why where you can see that there will be more like scalar, next about tensor, next matrix, all I will cover today. So first, let's say that is scalar. So scalar is nothing else by a single number, that is 0 dimension single number. Example like let's say that is 5, 0.01 and -3. So if we look at this like nothing else by learning rate. Learning rate means what? That is used in the machine learning model or deep learning model. You can see that learning rate term and that bias as well, that bias term is there, or loss value. So if the loss value is too large, that means your model is not predicting well. But if your loss value is quite like good enough, then you can say means quite less, then you can say it is good, right? And scalar control how fast and how much the model learn itself. I can give another example as well, like what is a split ratio here, like you can see like 0.2. So then test split in machine learning, then 20% itself is used as a testing the model, and training you can say that is 80%. Next, vector is nothing else by the list of number. That example itself is 2. Next, let's say that is 4 and 6. So that what that is nothing else by its represent features or embedding. Embedding means what? That you can see as itself again the same, like you can every word in a thing you can tokenize itself, like you can I say that is I love Maggie, so I can convert this, I can tokenize it into multiple token like word or sub word. Like I can say let's say that is I is another word, and next love is another word, and then Maggie is another word. But when I'm saying that embedding itself, then I have to keep that I as another list of number itself. So like what embedding I'm talking about. So if I say let's say that is king has a let's say embedding, and then queen has a embedding, so they are quietly related. So that's why they will be in the same space there. And if I say let's say that is vector of king minus vector of male plus vector of female, that is nothing yet by vector of queen. I will show it in Wikipedia nearby. So next, let's say that is matrix. So matrix is nothing else by the table of numbers like in a row or column. So next, it stored the weight of neural network, and images are stored as a matrix of pixels. CNN filter are small matrices. So let's see. So I will say let's say what is a matrix. So matrix is nothing else by this, like let's say m cross n. So it has m row and it has let's say that is n column. So you can see that is from Wikipedia example, we can see that is nothing else by 2 cross 3 matrix. because it has a 2 row. In first row it has 1 9 minus 13, so it has 3 column itself. So you can see that I am talking about a term that is store weight of the neural network. So you can see what is it. So weight of the neural network in matrix. So you can see that it's very simple. Like you have this neuron itself, let's say that is x0, that is the input we have, and let's zx, and once again I can see that. So yeah, so its z is nothing else by what, that equal to wx plus b. So w is nothing else by weight vector, weight matrix sets itself, and that I am talking about. If I say, let's say that is of layer map n into this one, so with dimension m cross n, so that is m row and n column itself, or it can be different as well, n cross m, but the point is that it is used in a forward propagation, that is z that equal to wx, that z that equal to wx plus b, b that is nothing else by bias vector. So let's see another term, that is images are stored in a as a matrix of pixels. So you can see that if I say black and white, then it is a 2D. Yeah, if you look at this one, that is very simple, that 8 this one itself, but if you look this one, that is nothing else by the pixel itself, but that is a matrix, because if you look that one, then it has a merely many matrices itself, that let's say 255 that is represent, that is white hair, right, and 0 represent that black hair. So that's the dimension I'm talking about, and that is actually a digital images are stored as a 2D or 3D matrices. But if you look a color image, then it is different, but it is a grayscale image, that's why it is a 2D matrix, where 0 represent black and 255 represent white. That what I am talking before, and intermediate value represents shade of gray. And if I say color itself, then it's go to RGB, then it is 3D matrix set itself, where each pixel has a three value representing the density of red, green and blue itself, RGB. So let's see the next term itself, that is CNN filter are a small matrices. So if you look at CNN filter, then this is I'm talking about, that is nothing else by that kernel or filter, that is combination kernel in CNN. You can see that if I look at it very clearly, then yeah, this one, right. So what happened here, nothing else by it is a multiplication of itself. So you can see that is 5 cross minus 1, then 0 cross 2 plus 1 cross 6, so that is all multiplied, and then we have a value that is 5 here, right. So you look at this one, this scenario, so it is also a matrix, nothing else by combination filter or kernel itself. And next what I am talking about, nothing else by tensor itself. So tensor is nothing else by general form of data, scalar, that what I say before as well, that is one value itself, that is nothing else by this 5 0.1 or 3. So that is 0D, that is 0 dimension. And if I look at that itself as 1D, then it is a one dimensional vector. Matrix is a 2D tensor, image is a 3D tensor. It is nothing else by height cross weight cross, that is channel. Video is a 4D tensor. Next we will go to matrix addition, that is very same, that is possible when shape are same, element wise addition. So let's see that. So addition, right. So it's A is a matrix where 1 3 1 and 1 0 0 is there, that is 2 cross 3, and it also B should be 2 cross 3 to do so to the addition. So it's like nothing was 1 plus 0, that is 1, then 3 plus 0, then 3. So it is element wise addition. So 1 plus 5, that is 6, and go on, right? So it is a result of it. So a plus b, that equal to obviously b plus a. So if you addition both ways, then it is the same result. And I said before as well, that is it is used when using bias in the neural network and using residual connection. So let's see that is how it is done using residual connection. So So it is nothing else by this part, that is y that equal to fx plus x. So here we are adding that is fx with x. So x is nothing else by my input input this one matrix, and that is fx is nothing else by again another output of a block, right? So that is ResNet. Here we are using element wise matrix addition. So next let's see, that is matrix multiplication. That is very simple, that is column of the first matrix that equal to row of the second matrix. So if I have, let's say that is 2 cross 3 matrix, so it's in matrix multiplication the second matrix should be 3 cross 2 or 3 cross something, so where both number will be the same. So let's see a demo itself in a Wikipedia. So yeah, it's quite like this, that is 2 3 4 and 1 0 0, that is 2 cross 3, and it is 3 cross 2 b, that is 0 1 0 and this one. So it has to be what, that is 2 cross 0 plus 3 cross 1 plus 4 cross 0, that equal to 3, and then 2 cross 1000 plus 3 cross 100 plus 4 cross 10, that equal to 2340, and then similarly it is done in this way. So it is nothing else by the matrix multiplication itself. So next it's produced, that is weighted sum, and its core of neural network forward pass. Let's see that. So in that sense what I am doing, that is nothing else by x cross weight w, that is w plus b, that is w nothing else by weight matrix. So I am nothing else by doing here multiplication, that I want to say here. And in forward pass y, that is equal to sigma into this one. I will talk about sigma after that. That is nothing else by activation function. It can be ReLU, sigma, or anything other. And that is bias term, that is I am adding this one, that is bias matrices. So and that is y, that is the output itself, forward pass. Next, training means learning better matrices. So you know that in modeling itself, that is we are trying to get the better matrices itself. So that is in machine term we are trying to get this, and that is it. So next I will talk about, that is dot product and transpose. And so dot product I will show in Wikipedia. So let's say that I have two vector, that is a that equal to a1 a2 dot 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 an, and b that equal to b1 dot 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 b to n. So if I specify it with the orthonormal basis, if I do the dot product itself, that is a dot b, that is nothing else by sum over ai into bi, that is equal to nothing else by, that is a1 b1, that is what, that element wise multiplication and addition itself. So that's why it is done. And if I have an example, that is 1 3 minus 5, and then dot product itself with 4 minus 2 minus 1, then it will result in 3, this one. And where it is used, that is used in embedding and attention. So attention is very important chapter itself in AI, and you know a research paper called that is very important, that attention is all you need, that change everything from where GPT concept come here. So you can see that is dot product. So let's see that. So in this scale dot product formula, we see that nothing else by it is a similarity that is dot product itself is attention dot product. So in attention you see that is there will be three vector that itself, that is q, k and b, and this is doing that is dot product, that is q cross k itself, and divided by root over dk into v. This one is a dot product to compute alignment score, and which are then normalized to represent probabilities itself. And you can also try to check cosine similarity, another example itself. So like let's say that is cosine similarity, and it is also a dot product, quite like that is cos theta that equal to nothing else by a dot b by that is the root over of sum over a square into root over of the sum over b square. So that is nothing else by sum over ai into bi. So that is also a dot product that is used here. And cosine similarity is used here to find the distance itself. So what is the use cases you can find? That is used for measure the similarity between two non-zero vector by calculating the cosine of the angle between them. So let's see the next part, that is nothing else by transpose. So it is used in the back propagation and used in the attention mechanism. It's nothing else by what, that is convert the row into column. That means if I have, let's say that is dimension of a matrix is 2 cross 3, if I transpose it, it is nothing else by 3 cross 2 itself. So let's see a demo. Like let's say this is nothing else by this one. So if I a is itself, and if I transpose this, then it will be that is this one. So that I am talking about. So next, let's say that is used in back propagation attention mechanism. So let's say transpose I see in attention itself, like that this vector that I say before, that is k transpose. So that is here it is used. And if you look at itself like in back propagation, so then you can see that that is q into is k transpose, that is nothing is the gradient of the attention score that I say before as well. So yeah, that is covered. So next, let's say that inverse matrix, that is less important here because it is rarely used directly in any deep learning cases, but it is used in linear regression math itself. And if you look at identity matrix, what is it? Nothing else by it act like a number one for matrices. So identity matrix is nothing else by defining by a matrix B, where A cross B that equal to nothing else by A itself. So B, this is nothing else by an identity matrix. So use in the skip connection and stabilize the deep network. So let's see that. So it is invertible matrix. No, I don't need that. So next, let's say that is so it is identity matrix I1 1, I2 that is 1 0 0 1, I3 this one, IN dot 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 this one. So I have let's say 3 cross 3 matrices for I3 and n cross n matrices for IN, and where you can see that all that element wise 0 0, that is means you can see that is first row and first column element of it is nothing else but 1, and second column second row that is row and this is column, so nothing else but 1. So itself nth, let's say that is row and nth column itself, that is nothing else but 1, that is unit matrix itself. So next, let's see why it is used. That is used in skip connection and stabilize the deep network itself. So let's see that. So so you can see this is nothing else by ICA skip connection. So you can see this is x is multiplied with the identity to get is again nothing else by x itself. So that's why I'm saying that it is also used here. And why it is stabilizing the deep network, because it is mostly used to prevent that gradient vanishing gradient an issue and facilitate faster and more efficient conversion itself. That's why it is used, and I will cover it later. What is gradient descent problem, vanishing gradient descent problem. So let's see that what is inverse matrix. That is nothing else by, let's define a matrix that is nothing else by B such that A cross B, that is nothing else by I, that is identity matrix. So yeah, that is also I'm saying. So you can check that inverse matrix, invertible. So yeah, so that is this one, invertible, this one A, I can have this one, and then you can see this, that is nothing else by this one. So this B is nothing else, 2 3 2 2 is nothing else by my invertible matrix, that inverse of it. And next, let's say that is shape and rank. That is very important. Shape is nothing else by the matrix sizes, that is row comma column, that I say that is 2 cross 3 or something different, that is 2 row and 3 column. And rank show the amount of information, and where it is used, that is used mostly in PAF, that is parameter efficient tuning technique, fine tuning technique. You can see that is PAF. That is next, let's say that is rank. So parameter efficient fine tuning. So you can see that this is specifically low rank adaptation or rank R, that is a crucial hyperparameter that determines the dimension of the trainable low rank matrices add to the model. What is the point here? Nothing else by, you can say, a pre-trained model weight, that is W, and I am trying to fine tune, that is del W here, that is nothing else by B multiplication with B A, and that is B and A are small and trainable matrix because the rank is very small, and then we can fine tune that and fine tune the weightage, and from 1 billion or something we can also convert it to 32 bit or something less parameter itself. So that's why fine tuning LoRa technique is very important. And if you look at it's saying that is shape mismatches cause most ML bugs, that is true, and rank, that is related to feature richnesses. If you have maximum rank, then its feature is much bigger and you can have much more parameter in the model itself. So next, eigenvalue eigenvector, that is very important thing, and that is mostly used in the PCA, and you see that is principal component analysis, and that's help reduce the dimension of the data itself. And what is PCA is, you know itself, that is PCA, that is very simple technique, that is nothing else by doing I'm saying that it is reducing the dimension. So let's see a image here. So that is you can see that is we have a data itself, it has three features, x1 x2 x3, original space, that is 3 dimension, and we have a data. And then if we convert it into, let's say that PC1, that is nothing else by that is principal component 1 and principal component 2, and then we can get this value itself. So PC1 nothing else by the first principal component which has the highest variance, and next PC2 is nothing else by second principal component which has the next variance after PC1. And if you look at the eigenvalue and eigenvector itself, so that is also very simple, that if you look at this definition itself, then you can see that we have a vector, that is V here, which is called as eigenvector, and it is the eigenvector of the linear transformation T is a non-zero vector, and this is lambda is nothing else by eigenvalue itself. So that TV that equal to lambda V, that is the definition. So that an eigenvector V of linear transformation T is scaled by constant vector, that is factor, that is lambda, when the linear transform is applied to TV cross that equal to lambda V. So how to calculate it? That's very simple. That is determinant of, let's say that is lambda minus T minus lambda I, that equal to 0. And let's see that a demo, that's itself. So let's say that is Yeah, so this is the cases. Let's say that is a v minus lambda v that equal to 0, then a minus lambda I that equal to determinant of this that equal to 0. So from which I can get that is nothing as by, let's say that is the cases a here 2 1 1 2, and if I determinant this one and I solve the equation, then we get two values, that is lambda equal to 1 and lambda equal to 3. So at v that equal to lambda equal to 1 that equal to 1 minus 1, and v that is lambda equal to 3 that is 1 1. So that is important cases. So that is nothing as by the eigenvalue and eigenvector, which is mostly used in PCA. So next that is we come to near the slided. So let's see that is how linear algebra power AI. Neural network, that is matrix multiplication, CNN sliding matrix filter, LLM embedding, that is nothing as a vector, attention that equal dot products plus matrices. So key takeaway, that is very important. AI is not magic itself, which is nothing as well the math, which is important. So linear algebra is the language of AI. Mastering this, remove the fears of models itself. So that is all for today, and next we will talk about calculus for AI.